Alright, this is the first class of this series. Today we are going to introduce the history, basic concepts, and terminology of mass spectrometry. In this unit, you are going to learn the fundamental knowledge about mass spectrometry. We will talk about the isotopic composition of elements and their effects on mass spectra, and also the nominal and accurate mass of molecules and ions. So how can we identify a molecule? Well, mostly a molecule can be detected based on its certain property like absorption, like fluorescence, or conductivity, electrochemical, reflective index, etc. And then the main focus of this course, mass spectrometer, it can separate the ions using the mass to charge ratios. The first prototype of mass spectrometer was created by J. Thompson. He built the first instrument to separate ions by mass to charge ratio in order to investigate the electric discharge in gases and the charged gas phase species. This guy got the Nobel Prize in Physics in 1906. The basic setup of his instrument is composed of four parts: the ion source, colorimeters, planar capacitor, which create the magnetic fields, and the fluorescence screen that detect the movement of ion. So it's essentially when the ion enters this magnetic field, it carries a kinetic energy. If the kinetic energy is high, then the angle of this Y deflection will be small. Likewise, if the kinetic energy is low, then the degree of Y deflections will be small. And you may figure out that the degree of Y deflection correlates with the mass to charge ratio and the charge sign. If your ions carries a negative charge, it will go this way. And if your ion carries a positive charge, then it will go downside. And overall, the heavier ion can stay closer throughout the axis, while the lighter one will push further out. It's correlated with the kinetic energy. Here we are going to introduce a typical workflow of a mass spectrometry analysis. Say if you want to investigate the chemical contaminants level in certain matrix, like you went out in the field, you collect the water sample, you collect the soil sample, food sample. The first step you have to do is the sample pretreatment. In this particular step, you want to simplify your sample matrix. You try to retain your analyte, but get rid of unnecessary interference. Typically, you can use a solid phase extraction, liquid extraction, and a variety of different extraction technique to achieve this goal. And next, the extract will subject to a certain separation technique like a liquid chromatography, gas chromatography, or ion mobility spectrometry. And the third step is the detection or the mass analyzer. A typical component of mass analyzer is composed of the ionization source, mass analyzer, and ion detector. You can consider the mass analyzer as a filter, a mass filter. You can only allow the certain molecules with a certain mass to charge ratio to get through it. And lastly, we have a data system like computer to record the signal. And you can generate the mass spectrum, you can generate the chromatogram, etc. Okay, ionizations. We talk about the ionization in the mass analyzer. According to different types of analyze, you can select an appropriate ionization technique for your mass spectrometry analysis. So if your analyte is kind of element or isotope, then you may try to use ICP or GDTI, AMS, this kind of technology for the mass spectrometry analysis. If you are going for a small molecule or the large molecule, then you will select some other ionization technique. And roughly, this ionization technique can be classified based on the ionization itself, whether it can cause a fragment, whether it can keep the molecule as intact as possible or not. So if the ionization technique, the step will not fragmented the molecules, then it will be called as a soft condensed phase ionization. One of the typical example is the electrospray ionization, which is commonly used in the LC mass quantitative analysis. The other end of the spectrum is a hard gas phase ionization, which will broken the molecule. So essentially, you can create the fragments during the ionization step. And the typical example is the electron ionization or the chemical ionization. Okay, let's go through some fundamentals about mass, a unit and definition. The first one is a unified atomic mass, U. Unified atomic mass is 1/12 of the mass of a carbon. The unified atomic mass is equivalent to Dalton, which is commonly used in biomedical field, but it is not an SI unit. The second one is a mass to charge ratio. It is the ratio of the mass number to the charge number. And the other expression of this mass to charge ratio is Thompson. It's to honor the J.J. Thompson. But Thompson is also not an SI unit. Mass spectrum or spectra is a 2D representation of signal intensity and versus the mass to charge ratio with a x-axis. The base peak is the most intense peak in the spectrum. Say if we have the mass spectrum, the peak with the highest intensity, we will call this as a base peak. And the y-axis expression can be an absolute intensity or relative intensity. Although if it is used as a relative intensity, it will compare to the base peak or as a percentage. The basic, in the other word, the base peak is with a 100% relative intensity. Nominal mass. The nominal mass of a compound is its molecular weight calculated using the atomic masses of constituent elements taken as an integer. So the carbon is 12, oxygen is 16, etc. So with this, you can calculate nominal mass. The average mass is a mass calculated using a weighted average of natural isotopes for the atomic mass of each element. All right, keep that in mind. The third one is a monoisotopic ion mass. It is a mass calculated using the exact mass of the predominant isotope of each element. So this mass can be detected with a high resolution mass spec. So here's is a sample. Say if we have a glycogen. A glycogen has the formula of these. If you calculate with a nominal mass, it's 3,480. If you calculate with a monoisotopic mass, then it is 3481.5997. But if you calculate most abundant mass, then it's 3483.6048. If you calculate the average mass, then it's 3483.7806. So right now you have a little bit idea about what's the difference or similarity between a different terminology referring to a nominal mass, average mass, or monoisotopic mass. Atoms have the different isotopes. Say the atom E, we usually or specify its atomic numbers, the number of protons at the left down side, and the left hand upside, we will have the mass number, which is equal to the atomic number and the neutrons. So the only difference between the different isotopes is in its the number of neutrons. They all have the same protons. Take the carbon as an example. We have carbon 12, carbon 13, or carbon 14. They all have the same number of protons of 6, but with a different mass number. So the only difference is in the neutrons, the number of neutrons. And the stable isotope, referring to the isotope, is not radioactive. If the isotope is radioactive, can be decayed over time, then it is an unstable isotope. It cannot be called as a stable isotope. So the monoisotopic elements are referring to the atoms usually only exist in the form of only one single naturally occurring stable isotope, like fluorine, like sodium, phosphate, iodine, etc. The diisotopic element just literally referring to those elements exist naturally in two isotopes, like hydrogen, carbon, and nitrogen. X plus 2, like chlorine or bromine. X minus 1 is like lithium or boron. For those elements with several different stable isotopes, it's called polyisotopic elements. And the majority of the elements are grouped as a polyisotopic element because they consist of 3 or more isotopes, showing a wide variety of different isotopic distributions. And if you want to get into the detail, you can refer to the table 3.1 for representative example of each classification. So the isotope pattern. We talk about the isotope, but the natural abundance, they have a certain ratio with the first one and second one. Right? So for example, the chlorine, the most abundant one is chlorine 13, and the second one is the chlorine 37. For bromine, it's about the 50-50 distribution. I'll take our previous example, glycogen, as an example. The molecular mass is 3483.7806 gram per mole, right? But in the mass spectrum, you cannot see a peak at the mass to charge ratio of 3483.7806. It is because this number is calculated from the average of the abundance of different isotopic peaks. You can only detect the monoisotopic mass to charge ratio. Okay. So the monoisotopic mass is also referring to the exact ionic mass. Should consider the removal or addition of one or more electrons. Okay. So here's an example. The exact mass of a CO2 with an electron is I calculate with carbon and the oxygen, 2 oxygen, extract 1, subtract 1 electron. Okay, so it's 43.99. So in our natural environment, there's natural variations in the relative atomic mass, like carbon. Carbon is usually exists as C12, right? But we can distinguish different biosynthetic steps with C13 and C12 isotopic ratio. Usually it's in the range of 0.01085 to 0.01115. So we can use the isotopic distribution, isotopic ratio to trace a different origin, like a plant, like fish, like mammals, or can all distinguish by their isotopic patterns. So it usually expressed as a delta 13C or a thousand, right? You can calculate these with PDB standard. Okay. For example, the petroleum, coal, and natural gas have PDB delta within this range, but the carbon and mineral is also carbon, but the ratio is kind of different. So we can use these to distinguish a different form of biological steps, pathways, or a different origin. So here's an example. If we calculate the PDB, then our C4 planes have its own certain range, and CAM planes have its certain range, C3 planes have its certain range, and coal and petroleum is a different C13 to C12 ratio. With this kind of ratio information, we can distinguish a different source of carbon related to PDB. So how can we calculate isotopic distribution? Here we will use carbon as an example to demonstrate this whole process. So carbon is an X plus 1 element. So if we use R to express the probability or the abundance of C13, okay, so you can calculate based on this formula. So if now we have a molecule ion M, which consists of W carbon, and the probability of the carbon is C12 is expressed in 100 subtract C over 100. This form represents the probability of C12. So the first case is very simple. Every carbon is C12, so we can calculate the probability of monoisotopic ion Pn, and in the form of C12 can be calculated with this formula. And the second scenario is a little bit complicated. If this W carbon, there's one carbon exists as a C13, how can we calculate the probability? So if the Pn plus 1 will equal to C W1 and multiply with the probability of C13 and the probability of C12. There's 1 C13 and W minus 1 C12. So we can calculate the probability of N plus 1 with this formula. So we can expect the ratio Pn plus 1 over Pn with this formula. But that's a simple case. Let's use a real example. Say we have a compound with a 16. So the Pn plus 1 over Pn will be W is 60 multiplied to 1.1 and over 98.9, which is 0.67. So the abundance, if the abundance as mass to charge ratio 720, which is N, is 100%, then N plus 1 will be 66.7%. But how about mass to charge ratio 7 to 2? Which is kind of similar. We can calculate the formula with a similar idea, like the probability will be C 60 take 2, and 2 of them is the C13, and 58 of them is C12, right? So we can calculate Pn plus 2 and Pn with this formula, which is 0 0.219. So maybe you will consider that, okay, the natural occurrence of C13 is pretty low, makes no difference. But when you have a lot of carbon, then you will have a very significant effect on the isotopic distribution. Say if you have one carbon, the C13 is 1.1, C14 is 0, right? But if you have two carbon, the percentage will increase to 2.2. If you have a 10 carbon, the percentage will increase to 10 to 11%. And if you go up to 100 100 carbon, then n plus 1 will be 110%, which is even greater than your nominal peak. Okay, so that's the reason why the stable isotopically labeled internal standard require at least 3 carbon labels, because you want to distinguish your internal standard with your natural occurring or analyte. At least within C30, if you label 3 carbons, you will only have a 0.1% effect, which is minimum, will not have a huge impact on the quantitative analysis. So that's the reason why the internal standard usually requires at least 3 carbon labels. If you have 2, you still have 1 to 2% inference when your carbon number go up to 20. It is possible to visually inspect the isotopic pattern from the mass spectra, especially for those having obvious patterns, such as chlorine and bromine. The ratio of natural abundance of chlorine 35 to 37 is 3 to 1, and 1 to 1 for bromine 79 to 81. These figures demonstrate the effects of adding a single chlorine atom or a pair of bromine atoms. The addition of one chlorine atom would tilt the slope anti-clockwise, as highlighted in the red line. The addition of a pair of bromine atoms would add a parallel line. Isotopic pattern can also be incorporated into the workflow of substance identification. If we have the mass spectrum of unknown compound, we can first examine its isotopic patterns. If obvious isotopic patterns exist, then we can identify the number of chlorine, bromine, etc. to calculate the candidate patterns and propose a molecular formula to this compound. If no obvious isotopic pattern is observed, we can also estimate the number of carbons from the C13 peak intensity. This example demonstrates how isotopic patterns can be used as an initiative of substance identification. Here, I'd like to share an online calculator that can help you calculate the isotopic distribution of a compound. Here is the link, and you can only need to provide the chemical formula and specify the calculation method. Then the software will give you the isotopic distribution coming with a data table and a proposed mass spectrum. Very handy. Mass resolving power, or mass resolution, is an indicator showing the mass performance. Mass resolving power is defined as the mass over the delta M, and mass resolution is the ability of separating two narrow mass spectral peaks. Take this as an example. Say your nominal mass locates in 500 and dm delta m is the peak width, which can be defined using the 10% or 50% valley. If it is defined by 50% valley, then it is FWHM. For the high-resolution mass spectrometry, their mass resolution is usually greater than 10,000. Here is an example illustrating the concept of mass resolution. The upper panel is acquired using the resolving power of 1000, where there is a huge peak at 28.01 representing nitrogen radical. However, there is actually the other peak, a carbon monoxide in the peak of 28.01, which can be distinguished when using a higher resolving power of 7000. Likewise, xylene and toluene cannot be distinguished until the resolving power is increased to 20,000. Mass defect is defined as the difference between integer mass and exact mass, which can be calculated using this formula. Here, we list the exact mass, nominal mass, and mass defect for the common atoms. The other common applications of mass defect is Kendrick mass defect. Kendrick mass defect is often used in the petroleomic analysis. Essentially, the idea of Kendrick mass is considering CH2 as a single unit, so the IUPAC mass of a compound will be multiplied to 14 over the 14,01565, which is the exact mass. Then the Kendrick mass defect is calculated using the following formula. If the compound is purely composed of CH2, then the Kendrick mass defect will be 0. In other words, the Kendrick mass defect is derived from the functional group. The same concept can be applied to per and polyfluoroalkyl substance or PFAS analysis. The only difference is that we can have to convert the IUPAC mass based on the CF2 scale. By using this approach, we will be able to pinpoint the emerging PFAS species. Our previous work adopted this approach to investigate the PFAS species in the firefighting foam, and we did identify several emerging PFAS species by using the mass defect approach and the homologous series search. The presentation of mass spectra can be bars, profiles, and lists. The profile spectrum is the original form that we can obtain from the mass spectrum. If these data undergo data reduction, we can convert the profile spectrum into the bar graph spectrum. The intensity of bar graph spectrum can be shown using a tabular listing with mass to charge ratio and relative intensity. For instance, 758.9 is the base peak with 100% relative intensity, followed by 759.9 with 63.2% and 760.9 with 21.7%. Ion chromatogram. Chromatography is referring to the separation, which can be achieved using the gas chromatography or liquid chromatography. We will introduce these techniques in the following lectures. For a chromatogram, the x-axis will be time, retention time, the analytical time that we detect the molecule. If we collect the ion abundance as a function of retention time, then these are termed ion chromatogram. Total ion current is the measure of the overall intensity of ion production or of mass spectral output as a function of time. If the original data is processed by means of data reduction or bulk spectrum, using the summation of peak intensity as the function of time, then it is called total ion chromatogram. Total ion current chromatogram is an interchangeable term of TIC. Reconstructed ion chromatogram is derived from the intensity of a given mass-to-charge ratio or M/Z range plotted as a function of a time or scan number, which is a secondary information that is extracted from original data. Extracted ion chromatogram refers to a similar idea of RIC, but specially indicate a specific mass-to-charge ratio. Base peak chromatogram is a chromatogram obtained by plotting the intensity of the base peak detected in each of a series of mass spectra recorded as a function of retention time. How can we evaluate the performance of a mass spectrometer? We can use limit of detection or signal-to-noise ratio to communicate the sensitivity of a mass spectrometer. The limit of detection or detection limit is the smallest flow or the smallest amount of analyte necessary to obtain a signal that can be discerned from the background noise. The signal-to-noise ratio describes the uncertainty of an intensity measurement and provides a quantitative measures of a single's quality by quantifying the ratio of the intensity of a single relative to noise. Usually, the limit of detection is defined as a SN ratio of 3 and limit of quantification as a SN ratio of 10. We will further introduce the concept of sensitivity in our following lectures. This table summarizes the commonly used symbols in the area of mass spectrometry or chemical reactions. The black dot indicates the unpaired electron in radicals. The positive and negative signs refer to the positive or negative charge ions. Likewise, the symbols for positive or negative radical ions are also shown. These symbols usually specify the position of a cleavage that happened, which can be seen in the product ion spectrum to express the fragmentation pattern. We will discuss this later. Alright, this is for today's lecture. See you next time.